In this video, we're going to talk about a special kind of discrete distribution, and that is a binomial distribution. A binomial distribution is a probability experiment that satisfies the following requirements. It must have a fixed number of trials, meaning you must already know how many items you're going to choose, how many people you're going to look at. It can't be, well, this time I'm going to choose 50, this time I'm going to choose so many. In order to find this probability, you need to know and set ahead of time that number of trials. Each trial can only have two outcomes. These outcomes are considered a success or a failure. You're in one of two categories. When we're talking about successes or failures, we have to look at how the question is worded. For example, if we're talking about we want to know the probability of getting a defective item, then our success would be getting a defective item. Our failure would be getting a non-defective item. So let's look at that. So if we think about, we want the probability of getting defective items. The key here is whatever we're wanting to get, that is considered our success. Whatever the probability that we're given, whether it be the probability of an event happening, is somebody not wearing their seatbelt, and that is a binomial distribution because they do wear their seatbelt or they don't wear their seatbelt. You really have to look at how the question is worded. So the probability of getting a defective, would actually be our success. A non-defective would actually be considered our failure in this case because of the way the problem is worded. So in order to be a binomial distribution, you have two outcomes. You're either sick or you're not sick. You either wear your seatbelt or you don't wear your seatbelt. You're either male or female. You either flip the coin and you get heads or you get tails. These are binomial distributions because it's an either or. It's one or the other item. The third requirement for being a binomial distribution is that outcomes must be independent of each other. Meaning that whatever happens on the first trial has no bearing upon what happens on the second trial. What I mean by that is the probability that the first person that you ask wears a seatbelt does not change the probability of the second person that you ask. They're completely independent. They don't mix. It's not like when you were drawing cards and we draw one and do not replace it. That changes our probability. Binomial distributions are where we have to put it back. We have to do that replacement. Everybody has the same probability each time. So the probability of getting a defective item the first time and the probability of getting a defective item the second time has to be the exact same probability. And that's what it also means for number 4, is that the probability of success must remain the same for the experiment. So numbers 3 and 4 kind of go together because if you're independent, you're going to remain the same. And so each time the probability is going to be the exact same for these. Now let's look at some notation here because binomial distributions have a little bit of unique notation that we want to look at. When we're looking at this probability of S, or whatever you're wanting, like I put up here, probability of defective, just means the probability of a success. And then we have probability of F. S is a success, F is a failure. These are just the symbols that we use, just like we say the probability of getting a 3. And we always write that off to the side as the probability of 3. This is what we're looking at now, the symbols of it. Then what we have is the actual numerical value. The probability of getting a success is a lowercase p. That's the probability of getting a success. So a p is the probability of a success. And then for the probability of failure, we use a q. So this is the probability of failure, meaning how many times does it not happen. And apparently I cannot spell because that should have a ty. So what we're looking at is a p and a q. The q is always the opposite of p. Remember that probabilities in any type of distribution must add up to 1. Therefore, p plus q equals 1. And this is going to be extremely important because most of the time we're only given one part of it. We're given the p usually, and so we have to find q. How we find q is take 1 minus our p, 1 minus our probability of that event happening. Another thing that we need to notice here is our n. So we also have an n, and this is the number of trials that we're looking at. So how many times are we going to repeat this item? How many people are we going to interview? How many tests are we going to take? Things of that nature. N is always your largest number of your set because it's like how many people are in the classroom. Then we want to say X is the number of successes in trials. Okay. X has to be between 0 and n, meaning it can start at 0 and it can only go up to n. It cannot be larger than n, because you can't have more successes than the number of people you have. Think about your classes. There are, if you're sitting in a class, you might have 35 people in a classroom. So for that example, we would have n being 35. Those are students in a classroom. Okay. We'll say we want to know the probability of 20 passing the class. So X is equal to 20. That is students that pass. and that is students that are in your classroom. So of those 35, we want to know the probability of 20 of them passing. Now let's just say that you're in a history class and they told us that the probability of passing, the probability of a student passing is 72%. Okay? So 72% of the time a student will pass. Pretty good odds there. Now if we have 35 students in a classroom and we choose 20 of them we want to know what's the probability of 20 of them passing. So this would mean that our P is going to be 0.72, and that passing in this case is a success. So passing is a success. And in this case, failing is our failure. So if 72% of the time a student will pass the class, what percentage of the time will a student not pass the class? So this is passing. What we're going to do is we're going to take 1 minus 0.72, and that's going to be 28% of the time. So 28% of the time they do not pass the class. These are the numbers that you're looking for when you look at a problem. You need to know the number of trials, like we have here. You need to know, okay, how many successes are we talking about? And it could be that you're looking at least a number or at most a number. And we're going to take a look at some examples of that. You need to know the probability of a success and change that into a decimal. Make sure that you always change percentages into decimals. And you also need to know the probability of a failure. Once you know these numbers here, then we can look at how do we actually solve these items. Okay? So let's look at what the formula looks like. The probability of exactly X number of successes, like in our previous problem, 20 successes, out of N number of trials, our 35 from previous, looks like this formula. We have n factorial divided by n minus x factorial times x factorial times p, which is the probability of its success, raised to the x power, times q, which is the probability of failure, raised to the n minus x power. Now let me just tell you that these two numbers here will add to n. So your two exponents have to add up to be n, because you either have a success or you have a failure. So how many successes are you going to have, and how many failures are you going to have? You take the probability of a success and raise it to the number of successes that you're going to have, times the probability of a failure, and raise it to the number of failures that you're looking at, out of the total number that you have. Now, hopefully, this right here might look familiar to you. This is actually n choose x. This is a combination formula. So actually the probability of exactly x successes is equal to how many combinations there are times the probability of successes raised to the number of successes times the probability of failure raised to the number of failures. And you can use the formula in either direction, does not matter to me. But this is how you would use the actual formula to figure out the binomial probability. And you have to be very careful. This is for exactly x number of successes. So if it says at least or at most, we have to look at that and be able to tell, okay, at least means that number and greater, at most means up to that number. So we're going to have to add these. We're going to have to do this formula multiple times. Let's look at an example of what I'm talking about. So here we have a missile guidance system, has 5 fail-safe components. The probability of each failing is 0.05. Find the probability that exactly 2 will fail. Okay, this one's going to be a little bit more difficult. So we have to identify what we consider a success, what we consider a failure for this particular problem. Notice it says the probability of failing, and we want to know exactly 2 will fail. That is our success. So our success is that a component will fail. Not fail, but fail. So if our success is that a component will fail, a failure is that a component will not fail. And I realize that this does not make much sense because we're talking about successes and failures, but we're just really looking at what is the main topic that we're looking at, and it's the failing. So that is going to be our p-value, and then the not failing will be our q-value. So our p is going to be 0.05 because that's the probability that a component will fail. Our q is going to be 1 minus 0.05. So q is going to be 0.95. A couple of other things that we need to know out of this is how many total guidance systems or components are we looking at? Our n, we have 5 total components. So remember that n is the total number. We want exactly 2. So x is equal to 2. So we're looking for the probability that x equals 2, exactly 2. Okay? So let's put this into our formula with these numbers. And I'm going to go ahead and use the actual formula for the first one without the combinations right now. And that is going to be our n factorial divided by n minus x factorial divided by x factorial times our p, which is 0.05, raised to the x power, times our q raised to the n minus x power. Okay. Now I'll clean it up a little bit. And that's going to be 5 factorial. 5 minus 2 gives me 3 factorial times 2 factorial times 0.05 squared times 0.95 to the third power. Again, you have to make sure that your exponents add up to your n, your total number. So let's see what we get when we have this. If I do the 5 choose 2, that is going to come out to be 10. And you have to be very careful on this. You do not want to round very much. Actually, it's better if you can put this all in your calculator at once, because some people really like to round, and we don't want to round off anything at this point. You always want to save your rounding until the very end. Okay? So make sure that you're not rounding off too early or anything of that nature. Now, when I multiply these together, I'm going to get that the probability of exactly 2 components failing, let me move this down a little bit, is 0.021434375. I wrote down all of the numbers for right now, just so you could see what it was if you're checking yourselves in your calculator. Now, remember that probabilities are rounded to 3 decimal places. So I want to round to 3 decimal places right here, and I look at this number, it's less than 5, so the probability of x equal to 2 is 0.021. So the probability of exactly 2 components failing is 0.021. Again, make sure that you apply it back to the original problem. Let's look at another one that's still dealing with the missile guidance system. Here, again, we're still dealing with the 5 fail-safe components. So I already know that my n is going to be 5. My p was 0.05 and q was 0.95. Those were things that carry over from the previous part of the problem. Here we're looking at the probability that more than 3 components will fail. More than 3. So let's think about this. We have the possibility of 0, 1, 2, 3, 4, or 5 components failing when we have 5 components to begin with. If we want more than 3, that means we do not include the 3, because more than means we want either 4 components to fail or we want 5 components to fail. remember back from probabilities that the word or means to add. So what we're going to have to do here is we're going to have to find the probability that x equals 5 plus the probability that x is equal to 4. And we will have to add those two to see what we get, to see what the probability that more than 3 will fail. This is where it gets to be a little bit tedious and a little bit longer at times. Okay? So if we do it all together, we have the probability of 5 is going to be the 5 choose 5. All 5 of them are going to fail. Times 0.05. All 5 of them will fail. Times 0.95. If all 5 of them fail, I have none that do not fail. That is this part right here. Okay? Then I'm going to add that 5 choose 4 times 0.05 to the 4th power. Let me get that to redo there. To the 4th power times 0.95 and if I have 4 of them that fail, that means I'm going to have 1 that does not fail. So this portion is this. Okay. So when I do this out, and this time I'm going to do it all in the calculator at once. If you look back at the notes, you'll see how I did it out by hand. But if I do this all at once, 5 choose 5 times 0.05 raised to the 5th times 0.95 raised to the 0. This is going to give me 0.2345625. And then I get oh no, I missed a number there. Let's see here. 296,875. If I add those together, it becomes this. So whenever I round that to 3 decimal places, like all probabilities are, I get the probability of 0. So the probability that more than 3 components will fail, whenever I actually round it to 0, or I'm sorry, round it to 3 decimal places, probability that more than 3 components will fail is 0. There is a very slight chance that they will all, or more than 3 components will fail, but when we're looking at rounding it to 3 decimal places or percentages, it does still come out to be 0. So whenever you're talking about a more than situation, you have to remember that more than means larger than the number given. So more than 3 actually meant 4 or 5. And we have to add those. It's not just the 4, it's not just the 3, anything like that. It's larger than that number and add them all up. Okay? At times, you will be able to use a table. It is the binomial distribution table. So you'll want to look in the back of your book and find the page where this is on. But you cannot always use it. It only satisfies certain probabilities. There are some probabilities that you can use it for. You can't use it for all of them. So it's a great, helpful tool. I'm going to show you how to use it, but don't rely on it solely. Be able to do the calculations. Okay? So let's look at this example. Here is one part of the table. Now this table is several pages long because it starts with n being 2 and it goes up to n being 20. And for each one it has your n, and then it has the x's from 0 up to that number. Then across here are the probabilities that it can be used for. It can be used for 5%, 10, 20, 30, 40, 50, 60, 70, 80, 90, and 95%. So if you're given a problem that says 55%, can't use it. It has to be one of the percents or the probabilities that is exactly on here. Now you'll notice that there's a lot of blank spots. Anywhere there's a blank spot, substitute a 0 in there for. It means that it's a 0, or it rounds to be 0, just like our previous problem did. So anywhere there's a blank spot, that becomes 0. So let's look at this problem that we have. Public opinion reported that 5% of Americans are afraid of being alone in a house at night. If a random sample of 18 Americans is selected, find the probability that there are exactly 2 people afraid of being alone at night. So it gives us some information. 5%. And let's actually go ahead and talk about what is considered a success in this problem and a failure. So it tells us that this is being afraid of being alone. So a success is if you're afraid, and a failure is not afraid. So the probability of it being afraid is 5%, but remember we have to change percentages into decimals. So that means that I change it into 0.05. Probability of a failure is 1 minus that. So that becomes 0.95. Same probabilities that we had a minute ago, which is okay. We're going to take a random sample of 18 people. So that's my n. That's the total number of people that we're looking at. 18 people. I want to know the probability that exactly 2 people are afraid. So the probability that exactly 2 people are afraid, x being 2. When you're looking at the table, the exactlies are great. First thing you do is you say, okay, am I on the correct area for my n? Yes. Okay. Then you want to find your p. The p that we have is 0.05. So we are going to be looking at this very first column here. So we're going to be looking at this column right here for our probabilities. We ignore everything else. Okay, because those probabilities don't pertain to us. The probability that exactly 2 people are afraid, we come here and we find our x being 2. So the probability of x being exactly 2 is going to be 0.168. No other calculations do I have to do. I do need to make that into a complete sentence. So I say the probability that exactly 2 people are afraid of being alone at night is 0.168. Okay? The table, like I said, is very nice. It's very handy if our probability is on there. If it's not, we have to do the calculations, and that's why I'm showing you both types of calculations. Okay? Let's look at another example. Here, we're still looking at the being afraid of being alone. So we already know that n is 18, our p was 0.05, and our q was 0.95. At this one, we want at most 3. So think about, we have 18 people, and so we can have anything up through 18. 10, 12, 13, 14, 15, 16, 17, and 18. Okay? We want at most 3. At most means we include 3 and everything below it. At most means include that number and below. At least means go from the number above there and everything above. But at most means include that number and below. So for this one, we want the probability of 0 people plus the probability of 1 person plus the probability of 2 people plus the probability of 3 people. And how we write that is the probability that x is less than or equal to 3. Less than or equal to means at most. Okay? Now I'll be honest, I don't want to have to do 4 calculations if I can keep from it. Thankfully, this is one where I can go to the table and use the table. We are again using this column. This time we wanted to look at probability of 0, 1, 2, and 3. So what we're going to do is we're going to take those numbers and we're going to add them. So the probability of 0 was 0.397. Probability of 1 was 0.376. Probability of 2 was 0.168. And the probability of 3 was 0.047. When I add those, I get 0.988. So the probability of at most 3 people are afraid of being alone at night is 0.988. Approximately 99% of the time. That's a huge portion. Okay? But we want to look at that. So this one, we've already done an at least problem. This one was an at most problem. At most means take everything up to that number and include that number. At most means start from that number and go forward, but not including that number. Let's look at another one. This one is still the same thing. So we still have our N being 18, our P being 0.05, our Q being 0.95. But this time we want at least 3 people. So again, if we think about what our possibilities are, we can go all the way up to 18. 14, 15, 16, 17, 18. We want at least 3 people. So at least 3 means that we want more than 3. Or I apologize. At least 3 means we want 3 or more. So we want 3 or more people. We can do this a couple of different ways, because if I have to do this one by hand, I don't want to add up all of those. I'll be honest with you. Remember that your probabilities all add up to 1. So the probability that X is at least 3, we could do the probability of 3 plus the probability of 4, probability of 5, all the way up to the probability of 18. Again, if I'm doing the actual calculations, I don't want to do that many calculations. So what I can do is I can do 1 minus these others over here. I can do 1 minus these. So the probability of 0, probability of 1, and the probability of 2. I just have to make sure that I subtract each of those out. Okay? Because I'm taking those away from my entire 1. Because remember that this whole thing adds up to 1. If I take the probability of each one of these and add them, they all add up to 1. So if I divide it out in the center or at some point, I have to look at it as one side plus the other side equals 1, or take 1 minus. I can do it either way, it does not matter. This one again is one we can use the table for. And so whenever I come down here and look at this, I want at least 3. So that means 3 and more. So it means I want everything in that red box. And so I could add up all 3 of those, because remember that these are all zeros. And so when I do that, if I add those up, 0.047 plus 0.009, 0.001, I get probability that x is at least 3 is equal to 0.057. That's if I add them all up. Now if you did it a different way, if you did 1 minus these, you would get a slightly different number in that third position, and it's a rounding issue. It's fine. Tell me which way you're doing it. I'll accept it either way. It does not matter. Because remember, each one of these have been rounded off to 0, and so there's going to be some rounding issues. You show me what you added or subtracted though. Make sure you're always showing your work. So that's one of the big keys. Show your work. But this is an at least problem where we take that number and include it. In anything, we always want to look at the mean, the variance, and standard deviation for any type of distribution. So for the binomial distribution, this is specifically for the binomial distribution, the mean is figured by taking n times p. That is why it is so important to make sure you know what your p is. So for our cases, n has been 18, p has been 0.05, and q has been 0.95. So our mean would be 18 times 0.05, which would give us that the mean would be 0.90. This is for either, or actually this would strictly be for the Americans being afraid to be alone at night. You could do it for the example where we had the 5 components. The only thing that would change would be your n. Your p would stay the same. For variance, our formula is going to be sigma squared is equal to n times p times q. All you're doing is taking your mean and multiplying it by your q. So in our case, we have 18 times 0.05 times 0.95. So our variance would be 0.855. I took 18 times 0.05 times 0.95. And then remember, standard deviation is the square root of your variance. So it's the square root of n times p times q. So we have the standard deviation is equal to the square root of 18 times 0.05 times 0.95. So we have that the standard deviation is going to be 0.9. Actually, I need to make sure that I round this one to 0.9. And they both come out to be 0.9 when we round them. The reason I rounded my variance to 1 decimal place is because we're talking about whole numbers. Remember, our x values were in whole numbers because we are talking about number of people. and mean, median, mean, variance, and standard deviation all need to be rounded to 1 decimal place more than your x values. So please practice these. If you have questions, feel free to ask me.